Soapy detergents. They are usually called soap and are prepared from fatty oils. These soaps have a general formula of this or this. They are actually salts of sodium and potassium. So as you will notice, this part here, the CnH2n plus 1, is actually an alkyl group. And you remember, an alkyl group can be represented by the letter R. So essentially the general formula for soap is or we could represent it with the potassium counterpart. Pretty easy, right? Yes. Now let's get into more details. The preparation of soap. Soap is prepared by the hydrolysis of fat or oil using an alkali. The fat can be derived from animals and the oil can be derived from vegetable oil, or you can say plants. Some of the common vegetable oils that can be used in the preparation of soap is known as glycerol stearate. Do not worry about this interesting term because you'll find that it is very easy. The formula for this compound is as you can see, this part here repeats itself 3 times. So the alkali that is commonly used is usually sodium hydroxide. However, potassium hydroxide may also be used. So in this case, when these two react in the presence of water, a hydrolysis reaction takes place to form the soap and an alcohol called glycerin or glycerol. The formula of the soap is given here. And glycerol, which is written as as you can see, glycerol is actually an alcohol. So preparing soap is very easy. All you need is some fat or oil and a strong alkali such as sodium hydroxide. Some warming and stirring needs to take place in terms of the procedure, but generally this is the essential reaction that takes place. The process we just described is a hydrolysis process, but in chemistry, when fatty acids are hydrolyzed in the presence of an alkali, the process is known as saponification because essentially it makes soap. Generally, we could recap and see, since the fatty acid can be represented by R, COO, R, COO, CH2, CH, RCOO and RCOOCH2, any acid that has this formula, any fatty acid with this formula, can be reacted by a strong alkali such as sodium hydroxide or potassium hydroxide. Let us use potassium hydroxide this time and see. To give, well, soap, which would be and glycerol. Glycerol will still remain the way it was. As you can see here, the general formula for soap has been obtained. During the procedure of making soap, a lot of stirring needs to take place, and at one point sodium chloride is usually added. This process is known as salting out. Since glycerol easily dissolves in brine, which is concentrated sodium chloride, then sodium chloride is added so that it can dissolve in it, and then hot brine is added to the mixture and boiled. The contents are allowed to settle, and then the solution will contain mainly brine and glycerol, which sinks to the bottom, and soap that later floats on the top. The brine glycerol water mixture is drained off using a tap or decanted off, and the soap is left behind. Well, that is the way soap is made. Pretty simple. Did you know that, first of all, many years ago, soap was made from ashes and animal fat? Could you try to see? The ashes contain sodium hydroxide, and the animal fat, of course, gives us the fatty acid. The cleansing action of soap. The cleaning action of soap depends on the structure of soap. For example, a soap made of sodium stearate, like the one we described in the preparation, consists of an oil-soluble long hydrocarbon chain, which is the non-polar end, and the polar end, which is soluble in water. You remember it's written as C17H35 COO Na+. Now, if we draw the structure of this compound, we would eventually end up with a very long chain. These ones essentially represent the alkyl part, and eventually we have the polar end, which is very short. So at this point here, you have the short polar end, and on this other side you have the long hydrocarbon chain, which is essentially non-polar. From our previous lessons and previous chapters, we know that polar substances dissolve in polar solvents. So the polar end dissolves in water, and therefore it is known as hydrophilic, which means water loving, and the nonpolar end does not dissolve in water and therefore is known as hydrophobic, which could say water hating. It does not dissolve in water. Now that we know the structure of the soap molecule, we can be able to describe how the soap molecule is able to clean oily stains from clothes. Since the hydrocarbon part can be represented by R, we could just have this written as follows. And we know very well that the R part is the nonpolar end, that is a long hydrocarbon chain, and this other part is the polar part. The nonpolar end of the carboxylate ion is soluble in oil, and the polar end is soluble in water. When soap is added to water during washing, the nonpolar hydrophobic end of the carboxylate ions, they lodge themselves into the grease, while the hydrophilic ends, which is the polar end, stick out in the water since they are attracted to water molecules. The following diagram shows how this happens. So in the first case, we have the water molecules with the long chains. I'm just trying to draw. The little circles represent the polar end, and the zigzag lines represent the nonpolar long hydrocarbon chain. So if you have a piece of cloth here that contains some stain of dirt or oil stuck to it, the nonpolar end will dissolve in the oil, while the polar end will stick out in the water, and eventually will form something that looks like this. Polar ends will stick out because they are attracted to the water molecules, while the nonpolar ends will lodge themselves into the oil or grease. This is our piece of cloth. Now, a little shaking and agitation, that is scrubbing, of the material that is being washed causes enough carboxylate ions to stick into the grease particles and dislodge them from the fabric to form small droplets of water-loving ends poking out, called micelles. So eventually we'll end up with the grease with so many carboxylate ends, the nonpolar ends lodging themselves into the grease, while the nonpolar ends sticking out. And these are what are known as micelles. The micelles cannot coalesce or come together as they repel one another due to the charge on the surface. The charge on the surface makes them repel one another, so they cannot form lumps or clogs. They are washed away during rinsing, and you remain with a clean cloth. I hope you understood. The effect of hard water on soap. From chapter 1 we learned that hardness of water is caused by calcium ions and magnesium ions present in water. These ions react with the soap molecule in a precipitation reaction to form scum. Well, since hard water contains calcium and magnesium ions, the soap added needs first of all to undergo precipitation and remove all the calcium and magnesium ions before it could form lather. And that is what causes water hardness. However, when you look at the equation, you'll find that soap, which is sodium stearate, reacts with calcium ions present in hard water to form an insoluble calcium stearate. This is what floats on the surface of the water in form of scum. Magnesium ions would react in a similar way to form scum as well.